Well, hello, honors class. If I got this set up right, you should both be seeing and hearing this video. Today we are going to start Chapter 13, States of Matter, and that is on page 340. So, grab your book and let's follow along. Page 340, Chapter 13, States of Matter. First thing is, we want to talk about pressure properties of fluids. So, properties of fluids. First of all, I am going to get used to writing here someday. First of all, fluids. Fluids are both liquid or gases. Fluid is going to be both liquid and gas. Okay? A fluid is both a liquid and a gas. So when you hear the term fluid, it's common to think of it as being just liquids, but remember, it can be either a liquid or a gas, okay? That said, the types of states of matter. Well, you probably already know this, but matter can exist as a solid. A solid we will define as an object that has a definite volume and it has a definite shape, right? If you think about any solid, look at your iPad. The iPad has a definite volume and a definite shape, okay? That's a solid. Okay, the next state of matter is the state called liquid. Liquid, well, you know what those are. Water's a liquid, for example. Liquids have a definite volume, but they do not have a definite shape. No definite shape, okay? A liquid, if you pour a liquid into a square cup, you have a liquid that is in the shape of a square. If you pour liquid into a round cup, liquid is in the shape of a round thing. So in both cases, the liquid has some volume. It's 1 pint, 12 fluid ounces, whatever your volume is, but it takes on the shape of whatever the container is. Okay? A gas. A gas has no definite volume and no definite shape. Think about the gas in the room you're sitting in right now. The air in the room you're sitting in right now is the volume of that room, and it is the exact shape of that room. If you were to take that air in that room and somehow put it into a different room, it would take on the shape of the new room, and it would take on the volume of the new room. So as such, gas has no definite volume or definite shape. It takes on the volume and shape of its container. Okay? Solid, liquids, and gases. All right, next. Here we go, next thing. If we look on our book on page 342, we'll start talking about the concept of pressure, okay? Pressure is force per area. Pressure is force per area, okay? Pressure is the amount of force you exert on something divided by the amount of area through which you are making contact. So example, if you push your hand up against the table and you push down on the table, you are applying some force with your hand, okay? The contact area is going to be the area of your hand. However much of your hand is touching the table is the contact area, and that would be A in that equation. So you take the force you're applying divided by the amount of area through which you're making contact, and you get pressure. Force is in the units of newtons. Area is in the units of meters squared. So the units for pressure are a Newton per meter squared. We're going to give that the special unit, the Pascal, and we'll use pascals. Occasionally you hear the term atmospheres as a unit. For example, standard atmospheric pressure or 1 atmospheric pressure. So you might see ATM as a unit. Well, 1 atmospheric pressure is 1 times 10 to the 5 pascals in our preferred units. Another unit you might hear for atmospheric pressure might be 14 pounds per square inch, for example. Okay? 14 psi. Okay? At any rate, there we go. Pressure is in pascals, and it's some force per area. Okay. Another way to think about this is imagine something like a balloon, right? You can think of the force as all the air particles in the balloon are going to be constantly banging against the surface of the balloon. So every time they bang into the balloon, it exerts some force on that balloon. Well, the area would be the surface area of the balloon. So you've got the air inside pushing on the inside of the balloon, and that force divided by that area gives you the pressure inside the balloon. Okay? Cool. All right, so that defines pressure and some of its units. If you look on the page 343, you'll see example problem 1. I've got it here in the video. I circled 2 unit conversions and wrote the word eq because the book seems to have made a mistake with the unit conversion. So when I solve this problem, watch out for that unit conversion. They're wrong. There are 10,000 square centimeters in a square meter, okay? So just watch out for that. Anyways, the problem says, a child weighs 364 newtons and sits on a 3-legged stool which weighs 41 newtons. The bottoms of the stool's legs touch the ground over a total area of 19.3 square centimeters. What's the average pressure that the child and stool exert on the ground? And B, how does the pressure change when the child leans over so that only 2 legs of the stool touch the floor? Who wouldn't want to lean back on a stool, right? All right, so let's go do this problem. Oops, hold on, I made a mistake. There we go, erase that. Moving on. Oops, made the mistake again. Oops, made the mistake again. Erase that. There we go. All right, so the problem. We are trying to find the amount of pressure. We are trying to find the amount of pressure, which is going to be the force exerted divided by the area, okay? We were told that the child weighs 346 newtons and that the stool weighs 41 newtons. So the total weight, or I guess we should just say, so the total force, right? The weight is just going to be the force of gravity. So the total force would be those two added together, which makes 405 newtons, okay? So 405 newtons, that's the weight of the child and the stool. That's going to be the force. The area is going to be the area of the 3 legs. So the area, we were told, is 19.3 square centimeters. Now, of course, we want square meters. So 1 square meter is 10,000 square centimeters, which gives me an area of 1.93 times 10 to the minus 3 square meters. So we take our force and divide it by our area. So pressure is force divided by area would be 405 newtons divided by 1.93 times 10 to the minus 3 square meters. And we get a pressure of 2.1 times 10 to the 5 pascals. Okay? For the second part of the problem, they want you to stand back on 2 legs. So, if you're on 2 legs, the area is just going to be equal to 2/3 of the original area. So the new area is going to be 2/3 of 1.93 times 10 to the minus 3. That'll give you the new area, okay, in meters squared. And now you can calculate the new pressure, the pressure exerted on 2 legs. Okay. Once you've gone through that problem and once that makes sense, I want you to go to the next page, page 344, and do problems 1, 2, and 3. You do not have to turn these in at this time. Go through those problems. If you have any questions, comment in the class discussion, shoot me an email. I'll see if I have to, I can upload some other content to get through this. But for now, work on those 3 problems. And I am out of here. Over and out.